Good morning, everybody. In the previous lecture, we have seen dot product, means scalar product of two vectors, and the examples on scalar product are dot product. Now today we are going to see projections. Let PQ bar and PR bar represents the vectors A bar and B bar with same initial point. With same initial point P. See, this is PQ bar and this is PR bar, so this is B bar, and PQ bar, this is A bar, and the angle between these two vectors is suppose theta. Or we have another position, PQ, and if this is PR, so this is A bar, this is B bar, and this angle is theta. Now see, PQ bar and PR bar represents two vectors A bar and B bar with same initial point P, because here the initial point is same. In this case also initial point is same. Draw the perpendicular from point R to the line containing PQ bar. Means from point R we have to draw a perpendicular, and that is meet the line containing PQ bar at M. Here also draw a perpendicular, that is RM, containing PQ bar, comma, meeting it at M. So this RM is the perpendicular drawn from R to the line of containing PQ bar. The scalar projection, of PR bar, that is A bar, B bar on PQ bar is magnitude of vector PM. See, magnitude of vector PM is nothing but the length of segment PM. So the length segment PM is called projection of vector B on A bar. Here also this PM is the projection of vector B on vector A. The scalar projection of B bar on A bar is magnitude of vector PM. Now see here, observe this figure. This PM, segment PM is the projection of B bar on A bar. In particular, projection of B bar on A bar is nothing but the shadow of B bar. Shadow of B bar on A bar if sun is overhead of B bar. If sun is overhead of B bar, then the projection of B bar on A bar is nothing but the shadow of B bar on A bar, and that is length of the segment PM, or that is magnitude of the vector PM. Now this is right angle triangle PMR. We know that in right angle triangle, what is cosine of theta? We know that cos of theta is equal to, see, this is theta. Cos of theta is equal to adjacent side divided by hypotenuse. See here, adjacent side is PM. So it is PM divided by hypotenuse. Here hypotenuse is PR. Now PM is nothing but the magnitude of vector PM bar, and PR is also nothing but the magnitude of vector PR bar. But PR bar is B bar, so which is equal to PM bar, magnitude of vector PM bar divided by magnitude of vector B. So from this one we can write magnitude of vector PM is equal to magnitude of, now shift this magnitude of vector B to left hand side, so we get magnitude of vector B into cos theta. So magnitude of vector PM is equal to magnitude of vector B into cos theta, means scalar projection of B bar on A bar, that is equal to PM bar, magnitude of vector PM, and it is equal to magnitude of vector B into cos theta. Now here we can multiply and divide to this expression by magnitude of vector A. So magnitude of vector A into magnitude of vector B into cos theta divided by magnitude of vector A. It is equal to, again see here, this numerator, magnitude of vector A into magnitude of vector B into cos theta, this is nothing but the dot product of A bar and B bar. So A bar dot B bar divided by magnitude of vector A, and this is scalar projection of B bar on A bar. Scalar projection of B bar on A bar is equal to A bar dot B bar divided by magnitude of vector A. Similarly, we can find vector projection. Vector projection of B bar on A bar is equal to vector PM. See, scalar projection is magnitude of vector PM, and vector projection is magnitude of vector projection is vector PM. Now again this vector PM can be written as magnitude of vector PM into A cap, where this A cap is, unit vector along A cap is unit vector along A bar. So vector projection of B bar on A bar is equal to magnitude of vector PM into A cap. Now where this A cap is the unit vector along the vector A, again it is equal to, we have just magnitude of vector PM, that is scalar projection of B bar on A bar, and scalar projection of B bar on A bar is A bar dot B bar divided by magnitude of vector A. So this is the value of magnitude of vector PM. It is A bar dot B bar divided by magnitude of vector A into A cap. What is A cap? It is the unit vector along A bar. By the definition of unit vector, this can be written as vector A divided by magnitude of vector A. Again, it is equal to A bar dot B bar into vector A divided by magnitude of vector A square. See, magnitude of vector A into magnitude of vector A become magnitude of vector A square, and this is the vector projection of B bar on A bar. So see, scalar projection of B bar on A bar dot B bar divided by magnitude of vector A. Vector projection of B bar on A bar dot B bar into vector A divided by magnitude of vector A square. So this is everything about the scalar projection of B bar on A bar and vector projection of B bar on A bar. See, direction angles. Direction angles. The direction angles of a non-zero vector. The direction angles of a non-zero vector A bar are the angles alpha, beta, gamma, alpha, beta, gamma that A bar makes with positive X, Y and Z axis respectively. See here, direction angles of a non-zero vector A bar is nothing but the angles made by that vector A bar with positive directions of X, Y, Z axis respectively. See, this is three-dimensional system, x-axis, y-axis, z-axis, and this is your vector A bar. Then the angles made by this vector A bar with positive direction means in this direction. This is alpha, this is beta, and this is gamma. So these alpha, beta, gamma, these are the angles made by the vector A with positive x-axis, positive y-axis and positive z-axis respectively. So these are called direction angles, and these direction angles determines the direction of vector A. These three angles determines the direction of vector A. So these are called direction angles. So direction angles determines the direction of vector in the space. The cosines of these angles are called direction cosines. Direction cosines of a vector A bar. Direction cosines are generally denoted by direction cosines are generally denoted by LMN. So we have L is equal to cos alpha, M is equal to cos beta and N is equal to cos gamma. So these are direction cosines. See, let I cap, j cap, comma k cap be the unit vectors along x, y, z axis respectively. It means that I cap is the unit vector along x axis, j cap is the unit vector along y axis, and k cap is the unit vector along z axis. Now the angle between a bar and x axis is alpha, so angle between a bar and unit vector I cap is also alpha, because I cap lies along the x axis. Let alpha is the angle between a bar and I cap. Alpha is the angle between a bar and I cap. We know that if we have a bar and b bar, two vectors, and theta is angle between them, then by using the dot product of these two vectors, we have a bar dot b bar is equal to magnitude of vector a into magnitude of vector b into cos theta. This is the definition of dot product. From this one, this can be written as a bar dot b bar divided by magnitude of vector a into magnitude of vector b into b is equal to cos theta. So if we have two vectors and angle between them is theta, then cos theta is equal to a bar dot b bar divided by magnitude of vector a into magnitude of vector b. Using this formula, here alpha is the angle between a bar and I cap, and also here given your a bar is equal to a1 I cap plus a2 j cap plus a3 k cap. Then what is cos alpha? Cos alpha is equal to, use this definition, a bar dot b bar. Now here a bar is a bar and b bar is I cap. So it is a bar, its dot with I cap divided by magnitude of vector a into magnitude of vector I cap. Again it is equal to a bar, this is a1 I cap plus a2 j cap plus a3 k cap, its dot with I cap divided by magnitude of vector a into magnitude of vector I cap. I cap is unit vector, so its magnitude is 1. It is equal to, see, this is first vector and this is second vector. In this vector there is only one component, that is ith component is there. So if you take the dot product of these two terms, so we get a1 I cap, its dot with I cap, प्लस बाकीच्या टोटल ज्या पुढच्या टर्म आहेत त्या झिरो होऊन जातील, फक्त एवढीच टर्म नॉन झिरो असेल, डिवाइडेड बाय मॅग्निट्यूड ऑफ वेक्टर ए. मीन्स दिस कॅन बी रिटन ॲज into 1, that is no need to write it. Again it is equal to, we know that a1 I cap dot I cap, this is 1, so a1 into 1 means a1 divided by magnitude of vector a. So we have cos alpha is equal to a1 divided by magnitude of vector a. Similarly, beta is the angle between vector a and j cap, and use this formula we get cos beta. Similarly, cos beta is equal to a2 divided by magnitude of vector a, and cos of gamma is equal to a3 divided by magnitude of vector a. So here we have the values of cos alpha, cos beta and cos gamma. So see, cos square alpha, we will take this, we have the values of cos alpha, cos beta and cos gamma. So cos square alpha plus cos square beta plus cos square gamma is equal to, see, cos alpha is a1 upon magnitude of vector a, so its square, it is a1 square divided by magnitude of vector a square, plus cos square of beta, cos beta is a2 upon magnitude, so a2 square divided by magnitude of vector a square. Similarly, cos of beta, that is a3 divided by magnitude of vector a, so a3 square divided by magnitude of vector a square. Again it is equal to, see, denominator is same in each term, denominator is same in each term, so it is a1 square plus a2 square plus A3 square divided by magnitude of vector A, bracket square. Again it is equal to A1 square plus A2 square plus A3 square divided by, see, we know that the magnitude of vector A is here, that is A1 I cap plus A2 j cap plus A3 k cap. So its magnitude is A1 square plus A2 square plus A3 square, and this bracket square. This square is here. Now this square and this square would get cancelled. It is equal to A1 square plus A2 square plus A3 square divided by A1 square plus A2 square plus A3 square, and this is equal to 1. So we have cos square alpha plus cos square beta plus cos square gamma is equal to 1. That is cos square alpha plus cos square beta plus cos square gamma is equal to 1. What are these cos alpha, cos beta and cos gamma? These are the direction cosines. These are the direction cosines of a non-zero vector A bar. So therefore direction cosines are denoted by L, M, N. So this is L square plus M square plus N square is equal to 1. And this is one of the relation between direction cosines. L square plus M square plus N square is equal to 1. Now, if L, M, N, these are direction cosines of a vector A, then the unit vector along the vector A is L into I cap plus M into J cap plus N into K cap. This is the unit vector A cap. This is unit vector A cap along the vector A. Means, see, if direction cosines are known, then from these direction cosines we can write the unit vector along that vector. If L, M, N are direction cosines of a vector A, then the unit vector along that vector is A cap, and it is Li into Mj plus Nk. So if this is A bar, see figure like this. See, this is your vector A bar, and it has direction cosines L, M, N. Then the line along this vector A, then the line along this vector A has direction cosines L, M, N. Now we see direction ratios. Also, see, this direction cosines also in short written as DCS. Direction cosines are also abbreviated as DCS, direction cosines. Now here we see direction ratios. Direction ratios. Direction ratios are three numbers. Direction ratios are three numbers which are proportional to the direction cosines. The numbers which are proportional to the direction cosines are called direction ratios. In general, direction ratios are denoted by small a, small b and small c. These ABC are direction ratios, and direction ratios are abbreviated as DRS, direction ratios. Similarly, direction cosines are abbreviated as DCS. Now, A, B, C are direction ratios, means A, B, C are three numbers which are proportional to the direction cosines. So therefore, L upon A is equal to M upon B is equal to N upon C, and it is equal to lambda, where this lambda belongs to R. It means that from this equation we can write L is equal to A into lambda, M is equal to B into lambda, and N is equal to C into lambda, where lambda is any scalar. So any line has infinitely many direction ratios. any line has infinitely many direction ratios but unique direction cosines. See once again, any line has infinitely many direction ratios but unique direction cosines. Now, so this A, B, C, these are direction ratios. L, M, N, these are direction cosines. Now, relation between direction ratios and direction cosines. Relation between DRS, direction ratios, and direction cosines. So let A, B, C are direction ratios and L, M, N are direction cosines. Then we have L upon A is equal to M upon B is equal to N upon C is equal to lambda. So from this relation, L is equal to A lambda, M is equal to B lambda, and N is equal to C lambda. But we have one relation, just as before some time we have seen that relation. We have L square plus M square plus N square is equal to 1. But now here L is A lambda. So it is A square lambda square plus B square lambda square plus C square lambda square is equal to 1. Now take lambda square common. So lambda square in bracket A square plus B square plus C square. It is equal to 1. It means lambda square is equal to 1 upon A square plus B square plus C square. That is, lambda is equal to plus or minus 1 upon square root of A square plus B square plus C square. Now put this value of lambda in this equations. L is equal to A lambda, M is equal to B lambda, and N is equal to C lambda. So therefore we have L is equal to plus or minus A upon square root of A square plus B square plus C square. M is equal to plus or minus B upon square root of A square plus B square plus C square. And N is equal to plus or minus C upon square root of A square plus B square plus C square. So these three relations gives us, these three equations gives us the relation between direction cosines and direction ratios of a line. Okay, this is the relation between direction ratios and direction cosines. See, we have a Cartesian coordinate system. X-axis, y-axis and z-axis. We have a line L dash. This is one line in the space. And we have two vectors along the direction of this line. This is OL and this is one another vector OL dash. So here let vector OL and OL dash are vectors in the direction of a line L dash. See, these two vectors are in the direction of L dash. Means this line L dash and these two vectors are parallel. Let alpha, beta, gamma are direction angles of vector OL means this angle is alpha, this angle is beta, and this angle is gamma. So these are the direction angles of the vector OL. Alpha, beta, gamma, these are the direction angles of vector OL. So therefore the direction angles of vector OL dash are, baga, see, this is the angle made by vector OL with positive x-axis. So this angle is alpha, so automatically this angle is pi minus alpha, because this total angle is pi and this is alpha, so this angle is pi minus alpha. So the angle made by vector OL dash with positive x-axis is pi minus alpha. Similarly, the angle made by the vector OL dash with positive y-axis is pi minus beta, and the angle made by the vector OL dash with positive z-axis is pi minus gamma. So the direction angles of vector OL dash are pi minus alpha, pi minus beta, and pi minus gamma. The direction cosines of vector OL are cos alpha, cos beta, cos gamma. Whereas you know that cos alpha, cos beta, cos gamma means, that is, you know that cos alpha is m, cos beta is m, and cos gamma is n. So that is L, m, n. Whereas direction cosines of vector OL dash are cos of pi minus alpha, cos of pi minus beta, and cos of pi minus gamma. That is minus cos alpha, minus cos beta, and minus cos gamma. But cos alpha is L, so that is minus L, minus m, minus n. See, the direction cosines of vector OL are L, m, n, and direction cosines of vector OL dash are minus L, minus m, and minus n. We know that the line L dash and vectors OL and OL dash are parallel. So either the direction cosines of line L dash are equal to the direction cosines of line vector OL, or the direction cosines of line L dash are equal to direction cosines of vector OL dash. So therefore the direction cosines of line L dash are either, म्हणजे बघा एकतर काय असतील ते, either L, m, n or minus L, minus m, minus n. So any line in the space has direction cosines L, m, n or minus L, minus m, minus n. So this is everything about the direction cosines and direction ratios. Today we have discussed projections of vector on another vector, in which we have studied scalar projection and vector projection, then direction angles, then direction cosines, and then direction ratios. Also we have seen relation between direction ratios and direction cosines. In the next lecture we see the examples on the basis of all these concepts. Thank you.